In this video, we discuss learning outcome number 4 for lesson 9.1, which is about constructing a confidence interval estimate of the difference between two population proportions. We're also going to describe the rationale behind the formulas and discuss the difference between the p-value and critical value methods and the confidence interval method for testing a claim about the difference between two proportions. So here is an outline of the confidence interval method. First, we want to check the requirements for using a normal distribution as an approximation to the sampling distribution or as an approximation to the binomial distribution. First, our sample data must form a simple random sample. So we'll have two samples, and both of them need to be simple random samples. Second, the samples must be independent. So there shouldn't be any natural pairing or matching between values in one sample and values in the other. And lastly, there must be at least 5 successes and at least 5 failures in both samples. That requirement needs to be met in order for us to use a normal distribution as an approximation to the binomial distribution. Then anytime we're doing a hypothesis test, it's important to state the null and alternative hypotheses. We usually do that by stating the claim in symbolic form. Then we say what's true if the claim isn't true. And then we look at those two statements, and the one that does not contain the condition of equality is the alternative hypothesis. And then the null hypothesis looks just like the alternative hypothesis. You just change whatever sign is there to an equals sign to get the null hypothesis. Okay, so then once we know what our null and alternative hypotheses are, the next thing we want to do with the confidence interval method is create that confidence interval. Now this looks like a lot of symbols. I see we've got 8 symbols on this line, but this is actually the same format as we've seen with confidence intervals for population proportions and confidence intervals for population means. It just looks like more because we're looking at a difference between p sub 1 and p sub 2. So this is the idea. Oops, sorry, I lost my mouse again. I hate when this happens. Let's see. All right, I'll try again. So, so this is the idea. The value that we're trying to estimate is this p sub 1 minus p sub 2. That's a difference between two population proportions. The way that we estimate that is we first come up with a point estimate of p sub 1 minus p sub 2. And that is given by p sub 1 hat minus p sub 2 hat. That's the center of our confidence interval. That's the best guess we have for what p sub 1 minus p sub 2 is. But it's very likely to be wrong. In order to get a better guess, it's better to have an interval estimate of what p sub 1 minus p sub 2 actually is. So in order to get an interval estimate, we compute what's called a margin of error, and that margin of error depends on the sample size. It depends on p sub 1 and p sub 2, or p sub 1 hat and p sub 2 hat. And it also depends on the significance level that we're interested in, or not the significance level, but the confidence level that we're interested in for this particular confidence interval. So this minus E and plus E is just where we're subtracting the error and adding the error. So even though this looks like a lot, and it is a lot, I just wanted you to see that this has exactly the same format as the confidence intervals had in the other sections. Just looks like more because instead of having just a mean and a sample mean, now we've got a difference between two proportions and a point estimate of a difference between two proportions given by p sub 1 hat minus p sub 2 hat. Okay, so that's our confidence interval formula. But in order to use that, we have to compute the margin of error, and we compute the margin of error this way. Notice we've got z sub alpha over 2. That's going to depend on the confidence level. As alpha increases, that z sub alpha over 2 increases. And then the second factor is an estimate of the standard deviation of the distribution of p sub 1 hat minus p sub 2 hat. Now, in general, that standard deviation should actually have a p sub 1 and a q sub 1 here, and a p sub 2 and a q sub 2 here. But we don't actually know what p sub 1 and q sub 1 or P sub 1 and P sub 2 are, or what Q sub 1 and Q sub 2 are, because we're coming up with an estimate of the difference between P sub 1 and P sub 2. Since we don't know those quantities, we're going to replace them with our best guess for what they are, which is this P sub 1 hat and P sub 2 hat. And if we're using those point estimates of P sub 1 and P sub 2, that P sub 1 hat and P sub 2 hat in this formula, it makes sense that in order to come up with an estimate for Q sub 1 and Q sub 2, we would use the point estimates for that as well. So this entire expression is an expression approximating the standard deviation of the distribution of P sub 1 hat minus P sub 2 hat. Notice that it's a slightly different formula from the formula that we used for our standard deviation in our test statistic for the p-value method and the critical value method. In our test statistic for the p-value method and the critical value method, the format was very similar. But remember, in those methods, we're assuming that the null hypothesis is true, which means that we're assuming that P1 and P2 are equal to each other. And if we're assuming that P1 and P2 are equal to each other, we're assuming they take on some common value. Now, when we're doing that hypothesis test, we don't actually know what that common value is. So our best guess for that common value is that pooled sample proportion P bar. So when we're coming up with the test statistic, which is created assuming that the null hypothesis is true, and then is telling us how extreme the particular value of P1 hat minus P2 hat is, given that the null hypothesis is true, the standard deviation looks just like this, but instead of P1 hat and Q1 hat and P2 hat and Q2 hat, the P's are replaced with P bar and the Q's are replaced with Q bar. And again, those represent the corresponding proportions, assuming that the null hypothesis is true, which is assuming that P sub 1 and P sub 2 are equal to each other. Or in other words, P bar, that pooled sample proportion, is our best guess of the common value of P sub 1 and P sub 2. While when we do a confidence interval estimate, we're not assuming anything about the relationship between P sub 1 and P sub 2. We're not assuming that these are equal to each other. So in this case, our best guess for what P sub 1 and P sub 2 are is P sub 1 hat and P sub 2 hat. I hope that helps. I hope that makes sense to you guys. All right, so after you compute your confidence interval estimate, you're going to use your confidence interval to make a decision about the null hypothesis. Now remember, the null hypothesis is that P1 is equal to P2, which is the same as saying that P1 minus P2 is equal to 0. So if the value of 0, that's P1 minus P2 is equal to 0, if that is in the confidence interval, then we're saying, well, P1 minus P2 might be equal to 0. So what we're saying again is that the null hypothesis might be true, or it may be true. If the null hypothesis may be true, then we're not going to accept the null hypothesis. We're not sure that P1 minus P2 is equal to 0, but since it might be true, we're going to fail to reject it. Now, if P sub 1 minus P sub 2 is equal to 0 is not in the confidence interval, we're saying that it would be very rare for us to get a P sub 1 minus P sub 2 that is equal 0. So this is suggesting that the null hypothesis is very unlikely to be true if that 0 is not in the interval. So in that case, we're going to reject the null. Another way of saying this is that if P sub 1 minus P sub 2 is equal to 0, if that is not in the confidence interval, what we're saying is that P sub 1 minus P sub 2 isn't 0. So if we're coming to some conclusion that P sub 1 minus P sub 2 isn't 0, that's another way of saying that is that P sub 1 is not equal to P sub 2. Well, in that case, we're saying that the null hypothesis is false, or we're not saying it's certainly false, but we're saying it's likely to be false, given our significance level. So in that case, we're going to reject the null hypothesis. Okay, so we look at whether 0 is in the interval or not. If it's in the interval, we fail to reject the null. If it isn't in the interval, we reject the null. And then we use that decision to come up with some final conclusion in terms of the original claim, in terms that everyone can understand, because someone should not have to take a statistics class to understand what we're talking about. Okay, so that's the outline of the method. Let's work an example. Now, this is the same example that we were working in the last two videos. We're just going to use a confidence interval method this time. So let me read the problem statement to you. It says, in a study of Burger King drive-through orders, it was found that 264 orders were accurate and 54 were not accurate. For McDonald's, 329 orders were found to be accurate, while 33 were found to be inaccurate. We're asked to use a 0.05 significance level to test the claim that Burger King and McDonald's have the same accuracy rates. This time we're asked to use the confidence interval method with a normal distribution as an approximation to the binomial distribution. Okay, so we start by checking the requirements. As in the last two videos, the requirements are met. We will assume that the sample data form two simple random samples. We'll assume that the samples are independent. There is no reason to believe that certain orders at McDonald's would be paired with certain orders at Burger King. And then we've got at least 5 successes and at least 5 failures in both samples. If we're thinking of success as an accurate order, I've got 264 that are successful and 54 that are not successful from Burger King. So both of those are more than 5. And then we have 329 orders that were successful and 33 that were not successful from McDonald's. Both of those are more than 5. So the requirements are met. Now, because we're doing a hypothesis test, it's always a good idea to state the null and alternative hypotheses. So we look at the claim. The claim says Burger King and McDonald's have the same accuracy rates. Or in other words, the proportion of accurate orders at Burger King is the same as the proportion of accurate orders at McDonald's. So that's saying that P sub 1 equals P sub 2. Since that includes a pure equal sign, it's just an equal sign, we know that that is the null hypothesis. The null hypothesis always uses an equal sign. So this time the null hypothesis happens to be the claim. If that's not true, we'd have P sub 1 is not equal to P sub 2. That will be our alternative hypothesis. Now, after we've done that, we want to compute the confidence interval. So the first thing we would do is compute P sub 1 hat minus P sub 2 hat. So for each sample, we're going to take the number of successes and divide by the sample size. This has already been simplified. We computed these in the last couple of videos, so I'm not going to go through it again. But again, we're just taking a number of successes, dividing by the sample size, and then simplifying to get this 44 over 53, and then doing the same thing for the second sample. And if you subtract those and use your calculator to estimate what that difference is, you get negative 0.07865 as an approximation to P sub 1 hat minus P sub 2 hat. Now that is our best point estimate for the true difference between the population proportions, P sub 1 and P sub 2. But we want not just a single point estimate, a single value, we want an interval estimate. So to come up with that interval estimate, we need to compute the margin of error. Now, the margin of error requires us to compute 2 factors. The first one is z sub alpha over 2. That has nothing to do with our sample, but it has everything to do with that significance level associated with our hypothesis test. Now, you always have to determine whether the original hypothesis test was a one-tailed test or a two-tailed test before you compute alpha. This z sub alpha over 2 in the formula, we have to be careful about it. It's not necessarily the alpha in the significance level. Sometimes it is. If it's a two-tailed test, the alpha in that is your significance level is the same as the alpha over 2 in this formula. But if it's a one-tailed test, that goes out the window. So I would rather that you not memorize that, but instead think through how we compute this z sub alpha over 2. So the first thing you do is you identify whether you're dealing with a two-tailed test or a one-tailed test. In this case, it's a two-tailed test. And then you look at the significance level of your hypothesis test. So the hypothesis test asked us to do this hypothesis test at a 0.05 significance level. Since it's a two-tailed test, that alpha equals 0.05 is going to be the area in two tails. So you are going to have alpha over 2 area in that top tail and alpha over 2 area in that far left tail. So alpha over 2, half of 5% is 2.5%. So this is a z sub 0.025. And then you can find the value of that using table A2 or using Excel. So let me show you how we would find that using table A2. Okay, so our alpha is 0.05 because it's a two-tailed test. That's going to be the area in two tails. So we're taking that alpha area and we're splitting it. Got 2.5% of the area under the curve up there and 2.5% of the area under the curve down there. Or we can write those in decimal form that way. If there's 5% in the tails, 95% of the area is in the middle here. Z sub alpha over 2 is this value. And the subscript again is the value of that area in that top right tail. So this is Z sub 0.025. In order to find this using table A2, I need to find the area to the left of my test statistic. It's always going to be 1 minus whatever that area is up there. Or you can take this 95% and add the 2.5% and you would get 97.5% of the area. So the area to the left is this amount. And so I'm going to look for this area to the left of 0.9750 in the body of the table and then find the corresponding z-score. Okay, so we go to our positive z-scores page and we're looking in the body of the table for 0.975. Up there it is. Do you see it? 0.975 is right there. That is in this row. So the first part of my z-score is 1.9. So z sub 0.025 is 1.9. And then the hundredths place comes from the header on this column. So we'll have 0.90, 0.91, 0.92, 0.93, 0.94, 0.95, 0. Or I keep saying 0. It's 1.96. So the corresponding z-score, the z-score that has this area of 0.975 to the left is 1.96. Now we can do that using table A2 as we just did. We can also use Excel. Now remember, when you're using Excel and you know the area to the left and you're trying to find a z-score, you have to use an inverse function. So you're going to type equals norm dot s, that's for standard normal distribution, dot inv. And if you open the parentheses there, Excel will tell you what it's looking for. It's looking for a probability. Again, probabilities are equal to, or probabilities correspond to areas under the curve, and we want the area to the left of this particular test statistic. So we want the value of z that will give us an area to the left of 0.9750, close parentheses, and it gives you that. And notice that if we round to 2 decimal places, we see that we get a z-score of 1.96. So we're getting exactly the same value with table A2 as we would get with Excel. Table A2 is probably what you'll use on an exam, but Excel is a great way to check your work and to easily compute these quantities while you're doing your homework or maybe doing some statistical analysis of your own. Okay, now after you have your z sub alpha over 2, the next thing we want to do is compute the estimated standard deviation using this formula. We're using p sub 1 hat and p sub 2 hat and q sub 1 hat and q sub 2 hat as estimates of p sub 1 and p sub 2 and q sub 1 and q sub 2. So we'll just substitute everything in. P sub 1 hat is this 50 or 45 over 53. And then q sub 1 hat is the complement of that. P sub 2 hat is this 329 over 362. and Q sub 2 hat is the complement of that. We take each of those products and divide by the corresponding sample size. The sample size for the first sample was 318. The sample size for the second sample was 362. So you can do this all by hand if you want to, and you would get, you can write this down and then type it into your calculator, and then you would get this as the estimated standard deviation. I want to show you how to use Excel for this as well. Now, if we're going to use Excel, we need to know what the sample sizes are for both Burger King and McDonald's. We're thinking of Burger King as our first population and McDonald's as our second population. And we're thinking of a success as an accurate order. So for Burger King, we had 264 orders that were accurate. So X1 is 264. Now be careful, N1 is the sum of the accurate orders and the inaccurate orders. N1 is the total number of orders. So it's this 264 plus the 54, which happens to be 318. Okay, similarly, for McDonald's, we have 329 orders that were accurate. So those are our successes. And then the total number of orders is the total of the inaccurate orders and the accurate orders. So we've got 329 that were accurate and 33 that were inaccurate, and that adds to 362. So those are the values that I'll use in my Excel spreadsheet. So I just go to Excel and I've just created a little table. N1 is the 264 plus the 54, which is that 318 that I mentioned. And X1 is the number of successes, so it's 264. N2 is 324. Don't forget your equal sign. So Excel will do your calculation. 329 plus 33. And the number of successes for McDonald's, the number of accurate orders is 329. Now P1 hat is the number of successes divided by that sample size. P2 hat is the number of successes divided by that sample size. And Q1 hat is the complement of P1 hat, so it's 1 minus P1 hat. And Q2 hat is the complement of P2 hat, so we type equals 1 minus, and then we select the cell for P2 hat. Okay, so now we want our estimated standard deviation for a critical value, or excuse me, not a critical value, for a confidence interval. So the estimated standard deviation for a confidence interval is equal to the square root. So you use the function sqrt in Excel of, open parentheses for that first fraction, it's P1 hat times Q1 hat, close parentheses, divided by the corresponding sample size. And then we're going to add the next quantity. It looks exactly the same, but you just change out the ones for twos. We'll have P2 hat times Q2 hat, close parentheses, divided by the sample size. Close parentheses for the whole thing, and hit enter, and you get this estimate of the standard deviation of approximately 0.0259. So that's the estimated standard deviation for our confidence interval. Notice that's exactly what I have here on this slide. So you can type this all into your calculator. You have to be very careful about order of operations. Make sure you put your parentheses in the right place. You should get this value of 0.0259. But I would highly recommend that you also use something like Excel. You have to be careful about the parentheses there as well. Excel is just going to do what you tell it to do. And if you put your parentheses in the wrong place, it might not. You might not be telling Excel to do what you want it to do. But if you're careful, you should get the same answer either way. Okay, so we've got our z sub alpha over 2. We've got the estimated standard deviation. The margin of error is that z sub alpha over 2 times this estimate for the standard deviation. So if we take the 1.96 and we multiply by this 0.0259 approximately, then we're going to get this answer over here. Now, I actually don't know if this number times this number is equal to that number. I actually did the estimation in Excel as well. So let me show you how I did that. I would type equals here in this cell, equals, And then I want the corresponding z-score, that z sub alpha over 2, and then I want to multiply by this estimate of standard deviation. Oops, I guess I forgot to keep that z sub alpha over 2 over here. So z sub alpha over 2 in this case is equal to this. Now remember how we calculated this. It was that norm.s.inverse function. And we said we wanted the area to the left to be 0.975. Yeah, I'll just type it that way. You could write this as a function of alpha. That way you could just change alpha on your spreadsheet and it would automatically update your z sub alpha over 2. So for a two-tailed test, our z sub alpha over 2 is this, which is approximately 1.96. Okay, so the margin of error is that z sub alpha over 2 times that estimate of the standard deviation. We get that. And that's what I have on my slide. Okay, now we've got the margin of error and P1 and P2. Let's compute P1 hat minus P2 hat. So we'll do P1 hat minus P2 hat. We get that value. And then for our confidence interval, the upper limit of the confidence interval comes from taking our point estimate P1 hat minus P2 hat and adding the margin of error. And the lower limit for our confidence interval comes from taking our point estimate for the difference, which is P1 hat minus P2 hat, and then subtracting the margin of error. And so we have these two values, and usually MyLab Statistics wants us to round to 3 decimal places. So when we round to 3 decimal places, we get an upper limit of negative 0.028 and a lower limit of negative 0.129. Okay, so our confidence interval looks like this. The true value of P sub 1 minus P sub 2, that's the difference between those two population proportions. Or in terms of Burger King and McDonald's, that's the difference between their accuracy rates. That true value is between a negative 0.129 and a negative 0.028. Okay, so that's our confidence interval. Now we're going to use that confidence interval to test our hypothesis, or to make a decision about the null hypothesis in this case. So we look at the interval and we think about whether or not the value 0 is included. And obviously 0 is not between this negative 0.129 and negative 0.028. Since the confidence interval does not include 0, that suggests that P1 minus P2 is not equal to 0, or in other words, P1 is not equal to P2. So we will reject the null hypothesis. Now, another thing that this confidence interval tells us is that P1 minus P2 is always negative. Now, the only way that that would happen, the only way that this difference would always be negative is if this second value was always greater than the first value. Does that make sense? Because we're taking a number and we're subtracting something that's greater than that. If we subtract something that's greater than that, we're going to get negative numbers every time. So that means that the second proportion seems to be, according to our evidence, greater than the first proportion. Now, the second proportion represents the accuracy rate of orders at McDonald's. So what this is telling us is that McDonald's has a higher order accuracy rate than Burger King. That's what that confidence interval suggests, because the values of P sub 1 minus P sub 2 are always negative. That means that P sub 2 is larger than P sub 1, which means that the McDonald's order accuracy is higher than the order accuracy at Burger King. Okay, now that was actually not what they asked us in the original claim. So we always want to go back to the original claim and state a conclusion in non-technical terms. So we are rejecting the null hypothesis, and the original claim was the null hypothesis. The original claim was that McDonald's and Burger King have the same order accuracy. So if our claim is the null hypothesis and we're rejecting the null hypothesis, what we're really doing is rejecting the claim. So the way we state our final conclusion is this. We say there is sufficient evidence to warrant rejection of the claim that McDonald's and Burger King have the same order accuracy rates. Now, this was a two-tailed test. It was not a one-tailed test, but the values of P sub 1 minus P sub 2 in that confidence interval actually tell us something about how that order accuracy rate at Burger King and McDonald's, how those two accuracy rates compare. The confidence interval actually gives us more information than the result of the hypothesis test. The confidence interval tells us that McDonald's has a higher order accuracy rate than Burger King, whereas our hypothesis test just tells us that there's sufficient evidence to warrant rejection of the claim that they have the same order accuracy rates. So our conclusion down here doesn't say anything about which one is more accurate. It just says that they're different from each other. But the confidence interval suggests that the McDonald's orders are more accurate than Burger King orders in general. Okay, so that is how we use the confidence interval method to test a claim about two proportions. Now, I actually don't recommend using the confidence interval method to test claims. Confidence intervals are better used for estimating differences between two proportions in this case. I would rather that you used a p-value method or a critical value method to test a claim and use the confidence interval method to estimate a difference between proportions. But people do use the confidence intervals to test claims about proportions, as we just did. Now, the p-value method that we talked about earlier, the p-value method and the critical value method, we saw that those are equivalent to each other. They both use the same estimate of the standard deviation to compute the test statistic z sub test, and therefore they yield the same results. In the p-value method, we're comparing probabilities or areas under curves. With the critical value method, we're comparing z values on that horizontal axis, but there is a relationship between the z values on that axis and the corresponding area under the curve. So the p-value method and the critical value method are giving you exactly the same results because they're using the same quantities and then comparing the values on the axis or the areas respectively. Okay, so we've got that. Now, you should know that in the p-value method and the critical value methods, we're assuming that P sub 1 is equal to P sub 2 because we're assuming that the null hypothesis is true. So in that case, it's appropriate, since we're assuming that P sub 1 and P sub 2 are equal to each other, to estimate P sub 1 and P sub 2 with the same value. The best guess that we have for that common value of P sub 1 and P sub 2 is our pooled sample proportion P bar. So our estimate of the standard deviation when we're computing that test statistic for the p-value method or the critical value method involves this pooled sample proportion be P bar because we're assuming that P1 and P2 are equal to each other, and we're saying P bar is the best guess for what those are both equal to. But with the confidence interval method, we're not using that pooled sample proportion P bar. So this method is not equivalent to the p-value method or the critical value method. Our estimate for the standard deviation used in the formula for our margin of error E uses P1 hat and P2 hat as estimates for P sub 1 and P sub 2. And those are appropriate here because we're not making any assumptions about the value of P sub 1 or P sub 2. We're not saying that they're equal to each other. We're not saying that they're not equal to each other. We're just trying to estimate the difference between P sub 1 and P sub 2 when we're coming up with a confidence interval. So it makes sense that rather than using something like a pooled sample proportion P bar, the best guesses that we have for P sub 1 and P sub 2 would be P sub 1 hat and P sub 2 hat. So that's what's used in the confidence interval method formula, and that's what makes the confidence interval method not equivalent to the other two methods. With the other two methods, we're assuming the null hypothesis is true, and that assumption leads to using this pooled sample proportion P bar as an estimate for P1 and P2. With the confidence interval method, we're not making any assumption like that. So we use P sub 1 hat and P sub 2 hat as estimates for P sub 1 and P sub 2. So what I'd like you to take away from this is that the confidence interval method is not equivalent to the other two methods because of the differences in the standard deviation formulas. Now, that means that if you are using the confidence interval method to test a hypothesis, you might obtain a different result than the result that you obtain from the p-value and critical value methods. The standard deviation is different in those two cases. Now, most of the time, they're going to give you the same result. They're often telling you to reject the null hypothesis at the same time or fail to reject the null hypothesis at the same time, sort of toward the boundaries, on the sort of the edge of those intervals. We might have one method telling you to do one thing and the other methods telling you to do the other thing. You got to be careful about that. So my recommendation to you is this: when you use a confidence interval, when you create a confidence interval, you want to use that to estimate that difference between two population proportions. It's assumed that that's what you're going to use it for. And that's why we don't assume that P sub 1 and P sub 2 are equal to each other. And instead of assuming that they're equal to each other, we estimate them with P sub 1 hat and P sub 2 hat. So use that confidence interval, but use it to estimate that difference between population proportions rather than testing a hypothesis. If you want to test a hypothesis, I recommend that you use the p-value method or the critical value method instead, because here we are assuming that the null hypothesis is true. And then based on the rare event rule, we're able to say something about that null hypothesis. So critical value method and p-value method, those were made for testing hypotheses. The confidence interval was not really made for testing a hypothesis, although people can use it to test hypotheses as well. So just keep that in mind, that if you have a choice, you want to use one of these two methods to test a claim and use the confidence interval to just estimate that difference between the two population proportions. Okay, so that's it for learning outcome number 4. I'll see you in the next video to discuss our options for testing hypotheses when the requirements for the other methods are not met.